What's up, everyone? So this is going to be the first video in a series covering Fourier series. Yeah, I mean, that's Fourier Inception. But for the first few videos, I'm going to be covering the orthogonality relations between sine and cosine. Later, we're going to actually see how this is useful for Fourier coefficients and how we can find Fourier coefficients, a sub n and b sub n. But we'll cover a little bit more of that later on. But in the first video, I'm just going to be evaluating the following integral, and that integral is going to be I equals the integral from 0 to 2 pi of sine mx sine nx dx. And if you were to look at this integral, I mean, it doesn't seem like it's that bad. It seems like, oh, I'll just use a u substitution. So the problem with a u substitution is that if I were to, let's say, u equals a sine function, then when I take its derivative, I'm going to get a cosine function. That's actually not something that's in my integrand, so that wouldn't work. The next part is that, well, I can probably use integration by parts, but I mean, you can try it, and you're actually going to notice that it doesn't really work here. So instead, we're going to be evaluating this in two different ways. So in the first way that I'm going to be using is that I'm going to be using trig identities, and then in the second way I'll be using the complex exponential form of sine and cosines, because later on we're going to do more of these integrals. But yeah, so my first assumption, knowing that we're going to be using trig identities for right now, is that m and n are actually integers. They're not just constants, they're also integers. And so if I were to try to use a trig identity, then if I were to Google it really quick, then you should come across something like this. You'll have these two different trig identities. So it's cosine y here plus or minus cosine x sine y. And then another trig identity that you're going to have is going to be cosine of x plus or minus y equals cosine of x cosine y minus plus sine x sine y. And honestly, I do not like this method, simply because it's a lot to memorize, which is why I very confidently say that I Googled in order to be able to find these two trig identities, and that's something that you shouldn't be afraid to use. So the reason I pulled up these two and I picked these two identities is simply because it most closely resembles my integral. And you'll notice that my sine identity actually doesn't really resemble it, because I have sine times cosine on both of my terms. So then this, by default, we're not going to use that. But instead, I noticed that I have a sine x here and a sine y. So then that means that I can somehow solve for sine x, sine y, so that I can make it look like sine mx, sine nx. And so that's exactly what I'm going to try to do. And because I have a positive sine x, sine mx, sine nx here, then I'm going to be solving for the positive over here. So if I were to solve for the positive, that means that I'm picking the negative argument here. So I have cosine of x minus y, and that equals cosine of x cosine y plus sine x sine y. And then if I were to solve for sine x sine y, then I get sine x sine y. All I have to do is just subtract cosine x cosine y from both sides, and I end up getting a cosine of x minus y minus cosine of x cosine y. And then I can just easily plug in mx for x and then nx for y, and then I'll get my integrand. But the problem with that is that if I were to use this exact identity, then I'll end up with the same exact problem, where I have two cosine functions multiplying each other, and then I can't really use any other method of solving for it. So instead, I keep persisting with the trig identities, and I basically say, well, I know that I just used up one of my identities for cosine of x plus or minus y. So instead, now I'm going to be using the other sign, which is cosine of x plus y, and I'll notice that I can just solve for cosine of x cosine y and then plug it straight into there. So cosine of x plus y will be equal to cosine of x cosine y minus sine x sine y. And if I were to solve for that, I get cosine of x cosine y is equal to cosine of x plus y plus cosine of x, sine of x sine y. And then I can plug this term straight into there, and I get sine of x sine y is equal to cosine of x minus y. And then minus cosine of x plus y minus, or plus, sorry, sine x sine y. And then distributing in my negative, I get a cosine x minus y minus cosine of x plus y minus sine x sine y. And then you'll notice that I have this term and this term. All I have to do is just add a sine x sine y to both sides, and I end up getting sine x, 2 sine x sine y equals cosine of x minus y minus cosine of x plus y. And then finally, I end up getting an expression that I can easily solve. Minus cosine of x plus y all divided by 2. And then if you notice that if I were to plug in the appropriate arguments into this x and y, I actually end up getting an integrand that is a lot easier to solve, or an integral that's a lot easier to solve. And that's simply because I don't need any kind of u substitution. I don't need any kind of special method to try to solve this integral. So let me go ahead and clear the screen for you guys. Okay, so all I have to do now is just plug in mx for x and then nx for y. And then you'll see that sine of mx sine of nx will be equal to cosine of mx minus nx minus cosine of, you'll see why I'm using these brackets in a bit, because we have some common terms, plus nx, and then all of this divided by 2. And then if I were to plug that into the integral, then I get that I is equal to the integral from 0 to 2 pi of, well actually we could just factor out this 1/2 to the front, and then we get a cosine of, and we can actually factor out an x, and then we get an m minus n x minus a cosine of m plus n x dx. And so yeah, this becomes a simpler integral to evaluate. Now before I actually start evaluating this integral, I'm going to be looking at the relationship between m and n. And so if we were to change m and n, then we're going to actually see that this integral ends up evaluating to something different. So let's say, for example, that I want to say that m and n like each other so much that they want to be like each other, meaning that m is equal to n. And so if I were to make that m is equal to n, if I were to make this assumption, then my integral is actually going to be a lot simpler, right? So then I end up getting I will be equal to 1/2 integral of 0 to 2 pi cosine of, well, m minus n gives me a 0, 0 times x is just a 0, minus a cosine of m plus n. So then we're going to have to pick between the two, m or n, but I'm just going to make them equal to L. So it's a lot easier to just say that we're just picking L. So then we have 2L times x dx. And the whole L thing is just a little substitution thing so that we don't have to pick between m or n. We just know that they're both equal to L. But yeah, so then this integral ends up reducing down to this, and then we get 1 minus cosine of 2lx dx. And so then this keeps going down, and now it's easier to integrate. We have a 1/2 x minus a negative sign, right? So that negative with this negative gives me a positive sine of 2l x. And then we divide by the derivative of the integrand, and that's going to give us over a 2L. And then we evaluate this expression from 0 to 2 pi. So plugging in our limits, we get a 1/2 and then a 2 pi plus a sine of 4 pi L divided by 2L. And then minus, if I plug in 0, I get 0. If I plug in 0 into here, I get sine of 0, and that's also 0, so we just get a 0 right there. Now, I want you guys to take a couple of seconds, a couple minutes, to try to see how this expression can actually be reduced down further. And one key thing to note is the assumption that we made at the very, very beginning of the video. And the assumption was that m and n are both integers. And using that is key information to be able to reduce down the expression that we have written down right now. So just go ahead and give the video a pause and see if you can figure out how to reduce this expression a little bit more. All right, so let's see if you get the same result that I'm about to write. And the result is that, well, again, we're using the key assumption that m and n are integers. And if they're integers, then that simply means that L is also an integer. That means that this expression here is, well, actually the 4 pi L is actually an integer multiple of 2 pi. And if you think about it, sine of 0 is going to be equal to what? Well, 0. Sine of 2 pi is going to be equal to 0. Sine of 4 pi is going to be equal to 0. And then if we keep going, you'll notice that any integer multiple, let's just say 2 pi times, I don't know, k, and k is also an integer, then you'll notice that the pattern continues through, and then that's actually 0. And if k is an integer and L is an integer, then that simply means that this expression is actually always going to be 0. And that's simply because L is an integer and 4 pi L is an integer multiple of 2 pi. And so then our expression actually ends up reducing down to pi. And so hopefully you guys got that final answer just like this. And I'm going to clean up the screen a little bit so that we can continue on with the video. Okay, so far we've seen that this integral I is going to be equal to pi as long as m and n are equal to each other. And well, what if we were to make the assumption that m does not equal n instead? What does that mean? Well, let's take a look. So actually, let me go ahead and rewrite the other expression for this guy. We had cosine of m minus n, and this was all here, x minus cosine of m plus n x dx. And so if they're not equal to each other, then that means that we're actually going to get a different answer. So the fact that we're saying that m does not equal n, then that must mean that m minus n is going to be some value. We'll just say that a is equal to m minus n, and then we'll also say that b is equal to m plus n. So then our integral ends up looking like this, and we get a cosine of ax minus cosine of bx dx. And then that's pretty easy to evaluate. So we get a 1/2 negative sine ax plus, right, because that's a minus cosine, we get a plus sine bx, and I can't forget to divide by a and b, and then we evaluate this expression from 0 to 2 pi. Okay, so then let's go ahead and plug in the limits. We get a 1/2 negative sine of 2 pi a divided by a plus sine of 2 pi b divided by b. And then using the same thinking as before, or well, actually not even the same thinking, it's just the mathematical fact that we have sine of 0 is going to give us 0 because of the lower limit, and then sine of 0 is also going to be 0, so then we just get this. And so then now we have a pretty similar expression as before, but instead of having L's, we have A's and B's. And if you look at this, well, if m and n are still integers, then that must mean that a and b are also integers. And just by looking at this, it should be kind of clear that m minus n is also going to be an integer. It's basically saying that 10 minus 5 is going to give you 5, and 5 is also an integer. So any two integers that you're subtracting or adding will always give you another integer. So then that must mean that these two guys will be going to 0. So then that means that I has two different results. I can either equal pi if m equals n, or it can equal 0 if m does not equal n. So then this would be our final answer. But before we actually say that this is our final answer, we can rewrite this expression in a nicer, more cleaner way. And that's actually using the Kronecker delta function. So that's actually a K. Hold on, I don't want to make it look like an R. Kronecker delta. The Kronecker delta is represented by a lowercase delta with the subscripts m and n, or l and k, or any it's just notation. But usually it's represented by delta with two subscripts. And the delta itself actually equals 1 and 0 if m and n equal each other, and then if m does not equal n. So 1 if m equals n, and 0 if m does not equal n. And if you look at this, this actually looks very, very similar to this. And so then we can rewrite I, and basically like we could just use a simple mathematical tool with just factoring out a pi, and then we get 1 and 0, and that's if m is equal to n, and then we get this if m does not equal n. And so then you can notice that we can just rewrite this expression as pi times delta mn. So this integral, the integral from 0 to 2 pi sine of mx sine of nx dx will be equal to pi times delta mn. And that is going to be our final answer. And again, really the Kronecker delta is just a different way of writing this piecewise expression. I mean, you can write this, but honestly, I'm sure that many of you guys have heard that physicists are very lazy and they just don't like writing a lot. So they end up coming up with notation that is universally accepted. And this is just one of those expressions where we use the delta, the Kronecker delta, to be able to indicate 1 or 0s based off of these subscripts. And so yeah, actually, really quick before I let you guys go, in order for you guys to really know how to use this notation is just by using the subscripts m and n. So let's say, for example, that m was equal to 4 and n was equal to 5. That means that you have the integral of sine 4x times sine 5x dx, right? And so then we know for a fact that m does not equal n in this case, simply because 4 does not equal 5, and so then this integral ends up evaluating to 0. But in general, if you were to basically say that this integral is just equal to pi delta mn, and you don't know what you're integrating, you don't even know that this is an integral, they're just giving you this expression, you know for a fact this is going to be 0, simply because if you were to plug that in, delta of 4 and 5 equals 0. Again, because we're using this piecewise expression right here. And so if we were to use delta sub 5, that's going to be equal to 1, simply because m does in fact equal n. And in the Kronecker delta, we never use decimal values. We always use integers. And usually we use integers simply because m and n actually represent indices. But again, this is just an introduction to this is the first video in a series that's eventually going to lead to Fourier series stuff. So stay tuned. Thanks, guys.